numerical differentiation. And the subsequent topic would be an integration. So we'll start with differentiation and then we will move towards integration. So when we talk about numerical differentiation, what basically it means. So let's say you are given a specific function and you know that function has a specific analytical expression. So for example, if you know the function is sine of x, let's say. So if the function is known to you, you know you can easily take the derivative of this function with respect to x, and f prime of x would be cosine of x, and so on and so forth. So you can basically take that and take the derivative of the analytical expression. But what if you don't know the analytical expression? So there are many instances in real life systems when you will have no specific intuition or idea about the actual function of a specific system, or specifically the model of a system you're trying to approximate. For example, let's say you talk about the velocity of a body. So you say the velocity of a specific rigid body basically you have the measurements of the velocity of a specific rigid body. So for example, if a rigid body is a block of mass m lying on a specific floor, which may be friction or frictionless, and it is moving at a specific velocity, then at different time t is equals to t naught, then at time t is equals to t1 seconds, and so on and so forth, you will basically get the measurements of the velocity by the sensors and instrumentation that you have. So what you essentially have is that you have a bunch of data points corresponding to the measurements of the velocity. So for example, if you have a time and you have a velocity, then at time t is equals to t naught, you have a specific velocity, t1, you have specific velocity, t2, you have specific velocities, and so on and so forth. Now, if you are interested to know the position of a mass at a certain function of time, or the acceleration of a mass or a block at a certain function at a certain instant of time, and then how to get that information. So you have this bunch of data points based on the measurements of the velocity. For example, you have the speed indicator, or basically a velocity indicator. You basically measure the velocities, and from there onwards, you basically are interested to determine the position or the acceleration. So any idea how can we determine that? Anybody? Any volunteer?
Form a function of the velocity and then we take the integral.
Yeah, so let's say the question, so I will come back to the point that you are mentioning, or the line you are basically uh, leading us to, or basically pointing us to. So the requirement is estimate position as a function of time A, and B is estimate acceleration as a function of time. So for the position, I think you were mentioning about taking the velocity and function and integrating with respect to time, right?
Correct.
Right. So basically what you have, velocity is time derivative of your displacement. That means if you want to integrate the displacement, you want to have velocity as a function of time. Now this will give you, this expression will give you the displacement. And if you know the integral from t naught to tn, which is from time t is equals to 0 to time t is equals to tn seconds, you can integrate this expression, and that will give you the displacement that a specific body achieves from, or specific body undergoes from time t is equals to t naught to time t is equals to t in seconds. Is everybody with me so far? Yeah, guys?
Yes.
Everybody is following what we are trying to do here?
Yes.
Now, you don't have this velocity as an explicit function of time. For example, I do not know velocity is varying linearly with respect to time, or I mean, for example, imagine that it is a specific vehicle and initially it was starting at 0 velocity, then it is accelerating, then basically the velocity graph, if I actually assume it actually accelerates and then it retains constant, so v is a function of time, it basically accelerates, then retains constant, I mean, remains constant and then deaccelerates to a 0 velocity, comes to a stop at time t is equals to 0. So time t is equals to t in seconds. Now, I do not know what is going to be the function. It may be linear or it may not be linear. So that is, if it is given, then you have precisely the expression of velocity at different time steps and you can calculate that integral. But if you do not know how the velocity is changing from time t is equals to 0 to say time t is equals to some seconds here and capital T1 here and capital T2 here. So if you do not know what is the rate of change of the displacement or how the velocity is moving, then you cannot perform this integral explicitly. So you cannot just have a specific, assume a specific function of velocity and integrate that. So what you have to do then is you have to use these data points or these measurements and perform numerical integration. So that will we will see. So we'll perform numerical integration. The same thing will happen when if you have to determine acceleration, which is time rate of change of velocity. Now in this case, again, I do not know what is going to be the velocity variation as a function of time. So if it is linear, then I know that it is just a constant slope. I can find the acceleration for that duration. But if I do not know, and if I know that there is no specific variation of, no specific variation has been mentioned. For example, these velocities are like this. Just let me point it like that. So velocities are like this. At time t is equal to 0, it is like this. And then v1 is here, v2 is here, then v3 is here, v4 is here, and that. So these are some data points that you actually gather based on these measurements. Now with these data points, how can I measure the acceleration? So then what we have to do is we have to perform what we call as numerical differentiation. But uh, before I actually go into the details of what the numerical integration techniques are and what the numerical differentiation techniques are, two things. First, are you guys following what I'm trying to describe here?
Yeah.
Is everybody on the same page? Everybody's following it?
Yeah.
Okay, great. The second thing is, given that you're following it and given that you don't know anything about numerical integration and you don't know anything about numerical differentiation, but with this given set of data points, you are asked to determine the acceleration at any instant, at any time within this interval. So how can you estimate acceleration, or how can you estimate displacement? Any idea that comes to your mind? You have the bunch of data points that comes from the measurement. So you basically have the set of velocity measurements at time t is equals to t naught and so on and so forth. So you got this bunch of data points, and without knowing any of the numerical integration techniques and differentiation techniques, you are asked to determine the acceleration. How will you do that?
Best fit curve.
Area under the curve, perfect. Now, where is that curve? I don't see any curve. It is just I'm seeing the bunch of data points. Where is the curve?
Use the methods we learned last chapter for best fit.
Yeah, of course. That is what you have to do. You have to basically fit a curve. And if you can fit a curve through this set of data points, let's say the data points, if you fit a curve, there are 1, 2, 3, 4, 5, 6 data points. What is the maximum degree of polynomial that fits through all these data points?
5.
5, fifth degree polynomial. So you can fit a fifth degree polynomial through this bunch of data points. And then what you have is you basically fit a curve that passes through these data points. And once you fit this curve, you essentially have a polynomial p of x or p of time. So p is basically the velocity as a function of time. You know exactly what the polynomial is as a function of time, isn't it? And once you have that polynomial, which is a fixed degree polynomial, let me call it as a naught plus a1t plus a2t square plus a3t cube plus a4t4 plus a5t5. 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. So I have 6 data points. 6 data points. I fit a fifth degree polynomial through this set of data points. And once I get that is basically going to give me an approximate or a polynomial that matches this set of data points. And I have got the explicit function. Now I can plug this explicit function over here to calculate the displacement, or I can use this function to take the derivative with respect to time to get the acceleration at any instant of time. Does it make sense, guys?
Yeah, it makes sense.
Yeah, I just had a quick question.
Go ahead.
For the homework, I recall doing some research that it's not really convenient to do the like really high order polynomials, instead to try to use the least amount.
Yeah.
So would you be able to also use like a trig function here instead?
So we will come back to a trig function, but trig functions are generally a class of functions which are called as Fourier series function or Fourier series terms. So I have not given you all the terms of the Fourier series in the homework. So basically that will not be valid in that case. But what you rightly pointed out is that if you have, let's say 6 data points, you are fitting fifth degree polynomial. If you have 10 data points, you have to fit 9th degree polynomial. So when and how to decide what is the polynomial, that right degree of polynomial that you should be using. So in practice, the best polynomial degree is cubic third degree polynomial. So in case you have to fit a polynomial, generally you tend to fit a cubic polynomial. Now you know that cubic polynomial requires only 4 data points, and I have 6 data points here. So how to fit a cubic? How do I fit a cubic polynomial through that? So one way is that in practice, use cubic polynomial. Now, either you can fit it through all the data points, or you can take 4 data points in the interval and you can fit a cubic polynomial that passes exactly through these 4 data points. For example, let me use some numbers. So for example, I have here 0 seconds. So this is my time in seconds, and this is in velocity. This is velocity in meter per seconds. So time t is equals to 0. I have velocity as 0. Time t is equals to 1 second. So it's 20. Time t is equals to 2 seconds. It's 25. Time 3 seconds. It's 30. Time 4 seconds. It's 35. And so on. 5 seconds. It is 50 meter per second. So for example, these are some of the data points. And if I am asked to find acceleration at time t equals 3.5 seconds. So I know that I have to determine the acceleration of the vehicle or the body at time t is equals to 3.5 seconds. What I can do, I can use this set of data points, 1, 2, 3, 4, 5, 6. I can pass a cubic polynomial. You know, we have used least squares technique or least squares regression technique to fit a lower degree polynomial to large number of data points. So that is one way. Another way is that you can take any four, 1, 2, 3, 4, any four data points that encompasses the 3.5 seconds, either this or this. So you can fit an exact cubic polynomial through these four data points or these four data points. And once you have got that polynomial, you can find what is acceleration by differentiating that polynomial at time t is equal to 3.5 seconds. Does it make sense, guys?
Yeah, it makes sense.
Yeah.
Use four data points to find a cubic polynomial. Then differentiate to estimate acceleration at time t equals to 3.5 seconds. Okay, so that is generally people do in practice so as to avoid overfitting. So if you use higher degree polynomial, there are always chances of overfitting. For example, if you have 6 data points and you tend to find an exact polynomial through these 6 data points, then your polynomial is a higher degree polynomial and it will overfit the data. Now, if there is some extra measurement you get, let's say from this 6 data points, extra measurement of velocity is happened here, then there is no way the polynomial can take this velocity into consideration. But if you have a cubic polynomial, then it basically tries to best fit and it tries to minimize the error in the measurement and the actual fitting polynomial. So that is what you can do. Did I answer your question? Sorry, who asked this question? I could not see the name.
That was me, Roosevelt.
Roosevelt. So did I answer your question, Roosevelt?
Yeah.
Okay.
Thank you.
So is it making sense to everybody here in the class?
Yes.
Yeah.
Yeah, great. So that is one method that instead of using numerical differentiation techniques or numerical integration techniques, you can use this set of data points, fit a polynomial. You can take all the data points, fit a highest degree polynomial through that, which goes through all the data points, or you can use a cubic polynomial spanning all the data points or any 4 data points. So depending on what your choice. And each of the approximation, again, these are all approximations. So each of the approximation will have some error, and the best will be that every method would, as I said, will have some error, but you have to basically select the best method which gives you the least error. And as I said, in practice, the general trend is to use cubic polynomial because it basically is a balance between overfitting and underfitting. So it basically tries to balance between the two factors. So that is one way, and we will come back to this specific interpolating polynomial. So one of the way you can fit that polynomial towards set of data points using least squares technique. You have used it in the homework problem. Excuse me. There are two other techniques. One is called Lagrange interpolating polynomial and Newton's divided difference. We will see in this class towards the end of the lecture. But right now, let's focus on how to perform numerical differentiation. So to perform numerical differentiation, what you have to do is we are given first a set of data points. This is your x and this is your function. And you know certain, so you know, let's say x minus 1, x0, and x1. So let's say the actual function varies something like that, and you have only 3 data points, x naught, x negative 1 as a subscript, which basically means a data point before x naught, and x1 is basically data point after x naught. So these are 3 set of data points, and the corresponding function values are your measurements that you have obtained from the sensor reading or from any instrumentation. And the actual function basically varies, something like that. So if you have to find the derivative at point x naught, so let's say the function derivative, the actual derivative varies like that. A tangent at x naught is this. This is the line which is your actual slope of the function at x is equals to x naught. But since I do not know the exact function, so I have no way to determine this actual slope. So instead, what I can do, I can approximate this slope by either using these two data points and passing a straight line through these data points, or I use these two data points, pass a straight line and say that that will be the slope, or I can use this neighboring data points and pass a straight line through them and say that will be my slope. So that is the graphical or the intuitive reasoning behind the numerical differentiation technique, but it analytically it all based on Taylor series expansion. So let's talk about what Taylor series expansion is. So for example, if you have to expand f of x plus h about fx, so the Taylor series expansion is given by f of x plus h times f prime x plus h squared by 2 factorial f double prime x and so on. Is everybody okay with that? So if I have to expand a function about x naught, then it will be f of x naught plus h is equals to f of x naught plus h times f prime evaluated at x naught plus h squared by 2 factorial f prime x naught and so on. Now this is a Taylor series expansion. It has got infinite terms and it depends on this expansion of the function value or the function about x naught. I mean, expansion of this function about x naught is based on the assumption that the function has got continuous derivatives. So it has got derivatives which are well defined and throughout the expansion terms. Now, I can truncate this series up to a certain terms. I'm saying that I'm only using second derivative and all the higher terms are neglected. So neglecting higher order terms. So this will be given by h squared by 2 factorial f double prime zeta. Zeta is basically a number which lies between x naught and x naught plus h. Does that make sense to you guys?
Still writing it down, but yeah, it makes sense.
Okay, so if I can write my Taylor series expansion by truncating all the higher order terms using this, where this is a zeta is any number which is between x naught and x naught plus h. H is your very small step size, so it is called a step size. So h is basically x1 minus x naught, or assuming they are all equally spaced data. So this is your h step size. And this is also your h step size. Or it is equals to x naught minus x negative 1. So depending on what you are, what interval you are considering. So if you're considering this interval, then xh is defined as x naught minus x negative 1, or if you're considering this interval, then it is basically x1 minus x naught. So it doesn't matter which interval you're considering, because the assumption here is that the data points that you are getting are uniformly spaced or evenly spaced data points. So the data points have uniform spacing. So H basically represents the spacing between the data points. So if that is the case, and I can write my function value like this in using Taylor series expansion, then if you look at this, it is basically saying that f of x naught plus h minus f of x naught, where x naught plus h is assuming I'm using forward difference. Forward difference means I'm using x1 and x naught data points, using x naught and x1. So x naught, f x naught plus h is f of x1 minus f of x naught is equals to h of f prime x naught. And this is a specific number which was given by h squared by 2 factorial f prime zeta. Or I can write f prime of x naught as f of x1 minus f of x naught divided by h minus h over 2 f prime zeta. So this is the 2-point forward difference formula for first derivative.
Can you please move the paper up a little bit more? Thank
Yes.
you.
Let me know if it makes sense to you guys. And what this formula is saying, so this is basically an error term, or assuming that I do not know what zeta is. At this point, I have no idea what the zeta is, but what I only know that zeta lies somewhere between x naught and x1 or x naught plus h. So it is somewhere, it lies somewhere in between these two numbers. So if I do not know the value of zeta, what I will do, I will approximate my first order derivative or first derivative as only this term, and I will say that this is my error. So my first derivative or first expression for the first derivative is this fx1 minus fx naught divided by h. And it has got an error, and that error has a specific order, which we call as order of h. Order of h basically means as h tends to 0, my error goes to 0. So the error goes to 0 at a rate of h. Let me see if there are any questions. Are you missing? So what is that? What is that factorial? Where is the factorial coming here?
Professor, I think they were talking about the box to answer where f prime of x naught on the right-hand term that's multiplied by zeta, there was no factorial sign within the box.
In this?
Yeah, on the right-hand side, the 2.
Okay, so yeah, 2 factorial is 1. Oh, sorry, 2 factorial is just 2. That's why I just used 2. So there is no, I just omitted the factorial. So I'm just expanding the factorial and writing it as 2. So that is 2 factorial is 2 times 1. That's it. Does it make sense, guys?
Yeah.
So this is the error. I mean, this is the error term, and error term basically varies with h, step size h. Basically what it says that as h tends to 0, so in the limit, so let's say if I say in the limit h tends to 0, then this approximation becomes an actual first order principle of the derivative. I mean, first principle expression for finding the derivative, which is f of x1, which is f of x plus h minus f of x divided by h, and this h goes to 0 because in the limit h tends to 0, this will be 0. So that will be the definition of the derivative from the first principles. Limit h tends to 0. This is what the actual definition of your first derivative is. Now, this is actually coming from the Taylor series expansion, wherein I have taken all the, I have neglected all the higher order terms, and this second order derivative will be defining my error, and that error will be varying with I mean, it is basically going to 0 depending on the step size h. So as h goes to 0, this error will also goes down to 0. So depending on how small this step size is, the accuracy of the derivative obtained using this expression will be matching the exact value of the function derivative at x naught. Let me know if it makes sense to you guys.
It does. Professor, can you go down to the bottom of the page so I can finish copying? A little bit lower, please.
Sure.
Thank you very much.
So this is called, this is basically known as forward difference formula because I'm using x naught. Let me know if you finish copying this, then that will explain you. I'll try to explain further. Have you finished writing?
Yes.
Yeah. So what it says that you are approximating this slope. This is actual slope of the function evaluated at x is equals to x naught. And this can only be obtained if I know the actual expression of this function. But since I do not know the actual expression of the function, what I will do, I will use some of the data points for this function, which I obtained using some measurements. For example, I know the velocity at time t is equals to 0, time t is equals to t1 seconds. And what I do, I use these two data points and pass a straight line through that, and that will define my slope. So that will be basically the approximate slope for using numerical differentiation using forward difference formula. Are you guys with me?
Yeah.
Yeah. Now there is another way you can find the slope, which is not using these two data points, but these two data points. And let me actually draw that again here. So I have x minus 1, x naught, and x1, f negative 1, f naught, f1, and instead of, okay, now somehow my function has changed because the way that I draw the curvature becomes a bit different. So let me actually come back to the original. So this is my actual slope. And instead of getting the actual slope, I use these two data points and pass a straight line through that. And that becomes my another approximation for first derivative. But this is going to be the approximation using 2-point backward difference. So what does basically this means that instead of using the Taylor series expansion of f of x plus h, I am going to use a Taylor series expansion of f of x minus h, and it will be f of x minus h times f prime x. Now here x is x naught, fx naught h prime f h prime, sorry, h times f prime x naught plus h square by 2 factorial f double prime zeta, because I neglected all the higher order terms. Now, if I solve this, what I will get is f prime of x naught is f of x naught minus f of x naught minus h, which is f negative 1, divided by h plus h over 2. Again, it's 2 factorial, you can say that, and f prime zeta. Again, zeta is not known to me. So the approximation of my first order derivative. Okay, it's somewhat out of focus here. So f prime of x naught can be written as f of x naught minus f of x naught minus h divided by h. So this is a 2-point backward difference formula. 2-point backward difference formula for calculating first derivative. Okay. So it basically says that I am not using these two data points, but I'm using the previous data point. So I'm interested in finding the slope or the derivative of function at x naught. But to find that, I want to use this point and another point which is coming ahead of this x naught, or which is coming before this time t is equals to t naught, or coming before this point, x is x naught. So x -1, x -1, and x naught. So I'm using these two data points and fit a straight, or basically draw a straight line, saying that will be my approximation for the first derivative. And as you see here, that both this forward difference and the backward difference formula has an error. It is not actually, nowhere it is basically resembling the actual slope. So what you can do is you can try to reduce this step size h, because your error, this is your error in that, this is the error of the approximation, or what is approximation in the first derivative. So this error will go down to 0 if the step size becomes very, very small. So if the step size becomes small, the error will disappear. And the rate of convergence will be linearly proportional to your step size. So rate of convergence means the error will go down to 0 depending on how my step size is varying. So if my step size is decreasing in a linear fashion, my error will also decrease in a linear fashion. Does it make sense?
Yeah.
Everyone here, are you following it?
Yes.
Any questions, guys? Okay, so if there are no questions, let me ask you then, is there any other way you can calculate or approximate the slope using these points you have? So I want to evaluate my slope at x naught. So this is my actual slope. So the forward difference formula says that you use these 2 points and basically draw a straight line as approximate the slope, or approximate the function derivative using the slope of this straight line. That is one way, and you call that as 2-point forward difference formula. Or you can join these 2 points and you call that as a 2-point backward difference formula. You approximate the derivative using the slope of this line. There is another way that you can calculate the slope, is there? And that is already, I mean, you can if you look at the graph, you can visualize that. And let me know if you are getting some idea about how else you can approximate the actual slope of the function at x equals to x naught.
Could you average the two slopes that you're determining?
That is one way you can say that, you can do that. There is another way that we can determine the slope. Any idea? Anything else? Any other idea you are getting? I mean, averaging out will make sense. I mean, it is one way, one method to do that, but there is another way to actually approximate the slope.
Between x -1 and x1.
Yeah. So you basically draw a line between x -1 and x1. So instead of using these and this, you draw a line between these two data points. And if you see that for this given example, you see that this data, joining a line between these two data points is much closer to the actual slope than any of the forward and backward difference formula. Does it make sense? Yeah. So instead of using this x naught and x1 and x naught and x -1, You are passing the straight line between x minus 1 and f1 and this one, x1 and f1. So you are basically passing a straight line through the endpoints, and we call that a center difference formula. So let me actually write the expression in a separate page. So f of x plus h is f of x plus h f prime x naught, all are evaluated at x naught, plus h squared by 2 factorial f double prime x naught plus h cubed by 3 factorial f triple derivative x naught plus higher order terms. Similarly, f of x naught minus h is f of x naught minus h f prime x naught plus h squared by 2 factorial f double derivative x naught minus h cubed by 3 factorial f triple derivative x naught plus higher order terms. If I subtract one function, if I subtract this from this, what do I get? So if I subtract this, what I will get is f of x naught plus h minus f of x naught minus h is, this will go away, 2h f prime x naught, this will go away, 2h cubed by 3 factorial f triple derivative zeta, neglecting all the other higher order terms. So this will become f derivative of x naught can be written as f of x naught plus h minus f of x naught minus h divided by 2h minus h squared by 3 f triple derivative zeta, where zeta is a number between x naught plus h and x naught minus h, and the approximation is called as center difference formula. So this is called as 2-point center difference formula, or some text also called it as 3-point center difference formula. To calculate first derivative. And let me actually draw the same.
Professor,
Yes.
the error term when you divide by 2h, you should still have 3 factorial, right?
No, 3 factorial is 6, and here it is 2. So it will be 2, it will be 6 actually. Yeah, it will be 3 factorial, it will be 6. You're right. Thank you. Center difference approximation. So what this says that you can also calculate the first derivative by not taking either the forward difference or the backward difference, but using a center difference and using again 2 points. So some text says that is 2-point center difference formula, but since you are using you are finding the slope of this function centered at x naught, so some text also call that as 3-point center difference formula, even though x naught is not function value at x naught is not used here, but some text also refer this formula as 3-point center difference formula. So, and this is basically a formula to calculate the first derivative at x naught. And the difference is that here the error is varying or is proportional to h square. So if you change the step size from h to h over 2, your error will eventually, basically will reduce by a factor of 4. If you reduce the step size by half, the error will reduce by 4 times of that, or basically it will be 1/4 of the actual error. So the convergence or the rate of the error going decreasing to 0 is much faster using center difference formula than either using 2-point difference formula or of 2-point forward difference or 2-point backward difference. In 2-point forward and 2-point backward, you see that this is the order is of h. The error varies with an order of h, but here the order of the error is h squared. That means the error is varying as proportional to h squared. So if you reduce the h by a certain factor, your error will be faster decaying to 0, or decaying to becoming more and more smaller at a faster rate. Does it make sense, guys?
Yeah.
Everybody is following so far, or do you have any questions? Please let me know. I will try to address that.
No questions so far.
Okay, so where do we use what approximation? So if I go back to the slide and I was showing the measurements at time t is equals to 0 seconds, I got a specific velocity. If I have to differentiate or find the acceleration at time t is equals to 0, let me ask you guys, can I use a backward difference formula? No. No, and why not? Because I do not have any values before time t is equals to 0, right? If I have to find, and if you refer to your notes and you see the backward difference formula, or let me actually show you using this slide. Backward difference formula requires what? If I want to find the slope at x naught, I need a value at x at previous time step or previous value. Does it make sense? But I don't have any previous value before time t is equal to 0 seconds. So I cannot use backward difference formula for estimating acceleration at time t is equal to 0. I can only use forward difference formula here. Similarly, at time t is equals to 5 seconds, I cannot use forward difference formula to find acceleration. I have to use backward difference formula because there is no other value after 5 seconds. Does that make sense?
Yes.
Yes.
All other intermediate points, I can use any formula I like. I can use forward difference formula, I can use backward difference formula, I can use